So in class today, we talked about molecular geometry. And just as a reminder, molecular geometry comes from the theory VSEPR, Zephyr theory, or valence shell electron pair repulsion. And that theory says that the electrons, whether they're lone pairs or locked in covalent bonds, because of Coulomb's law, want to be as far apart from each other as possible because they're negative. But they're locked in this molecule. So because of that, the molecule is going to assume a shape that is most energetically stable for it, given the fact that these electrons want to repel one another. And we have, that was bad. We have four primary shapes. We have a linear shape, and a linear shape can really form from three different ways. Obviously, this bond can be on the other side, but the characteristic of a linear shape is the lack of any lone pairs on that central atom and just two external atoms. So some examples of this, one is BeH2, the other one could be CO2, and another example of this is hydrocyanic acid, HCN. So notice that none of the central atoms have any lone pairs around them at all, and they all have only two around. And according to valence shell electron pair repulsion, that will force these atoms to get as far away from each other as possible. And the best angle for that would be that 180-degree bond angle that we see right there, most energetically stable form of that. The next one that we like to look at is bent. And bent has a bent shape. And what causes these bonds to bend here that are not there? Well, that's the presence of one or two lone pairs of electrons. So these lone pairs of electrons are flying around this thing three-dimensionally, and these bonds are going to bend away from those lone pairs of electrons. We can also have a situation that looks like this. Example, obviously water is an example, and the bent conformation of water we'll learn in the next topic really affects its shape. Sulfur dioxide is another one. So similarly to linear, there are two external atoms, but different than the linear, we have either one or two lone pairs of electrons on that central atom. Next one we can do here is planar. So we're going to add another atom to the outside, okay? But much like linear, there is no lone pair on the central atom. So it stretches out as much as it can, very symmetric. Example here is BH3. And another example here is formaldehyde. So notice that both of these situations do not have any lone pairs on the central atom, and they have three external atoms. Well, what's going to happen if we put a lone pair on that central atom? We're going to get the pyramidal shape. And that pyramidal shape has that lone pair on the central atom, which pushes those three bonds. So similar to planar, there are three external atoms. Not similar, there's a lone pair on the central atom here that pushes it away from that 120-degree bond angle down into a shorter bond angle. It turns out that this one is around 105 degrees. Don't need to know that, though. An example of that is ammonia. So when we did ammonia in class, I wasn't drawing it correctly, but I didn't want to focus on the bonds at that point, or on the shape. And the very last one is tetrahedral. I always think the game Tetris has different combinations of four boxes, and tetrahedral has four things. Come around. This is like the methane molecule. It's not a T, it's actually more of a tripod down here if you think about it, with that on the top. An example of that is methane. So notice, four things are on the outside, no lone pairs. So draw your Lewis structures and look up there at the top. One thing that I think some people might need a little bit of help on is how to draw ions. So let's focus on NH4 plus here for a second. So we have octet minus valence, So octet here is 8 plus 4 times 2 is 8. That's going to be 16 minus valence. Here we have 5 for N plus 4 for hydrogen minus 1 electron because it has a positive charge. Okay, that plus charge gets translated into a minus 1 because remember, losing electrons is a positive experience. So that becomes 16 minus 8, which is 8. So 8 divided by 2 equals 4. So it's simply NH, H, H, H. And we put it in brackets. Anytime you have an ion or molecule with a charge, we're going to put it in brackets. Okay? Or you could just say plus. And the shape of that's going to be tetrahedral. Let's do another situation where you might have a minus charge. So let's do something like NO3 minus or 1 minus. Okay, so we're going to do octet. It's going to be no exceptions here, so 8 times 4 is 32 minus valence. Okay, so here we have 5 plus 6 times 3, which is 18. And then we have plus 1. So in this case, that minus 1 gets translated into adding 1 because these things that we're counting, those are electrons. So now we have 32 minus 18 plus 6, so that's going to be 24. So 32 minus 24 divided by 2 is going to be 4. 32 minus 24 being 8 divided by 2, 4. So how do we draw that? Well, I'm going to go ahead and do it here. We have 3, but 4 bonds. This is happy, unhappy, and that one just needs 2. The whole thing needs to be in brackets with a 1 minus charge. 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8.